Okay, well, the contribution of this interval to the solid of revolution, as I said, is just the same as this, okay? Only difference being, for reasons we'll explain in a minute, I'm using an xi star instead of an x star. Because now I'm being more specific about dividing into n subintervals, and we don't have a notation to talk about the typical interval. So, volume of the solid of revolution is what? The contribution to the volume is going to be just this expression, but we're going to have an I in that x star, aren't we? By the same exact reasoning we used over here, this is it, okay? And I'm going to call that delta V sub I. The contribution of the ith interval to the total volume. Okay, well then the total volume will be the sum from I equals 1 to n, because, well, we want to add up all these subintervals. How many are there? There are n of them. We want to add up the volume that you get from the solid of revolution from each interval to get the total. Okay? Total volume is this. And that xi star is squared. Okay? Now, let's put a qualifier here. This is the total approximate volume that we get. So if we divide into 1,000 subintervals and actually calculate it, which we'd have to do if this expression isn't something we can integrate, we can easily do it. It's very easy to write a program to do that. As I say, anybody with decent mathematical background and aptitude, which is true for all of you, could learn that if you don't already know it, just in an hour. Okay? And then you could do this for any function, whether you can integrate it or not. Well, we haven't got an integral yet, so I might even talk about that. Let's see what the integral is. As n approaches infinity, this approaches an integral. And the integral, the thing you're integrating, has an integrand that looks just like this, except you drop the star and the I. Now again, this is for reasons that and the delta x becomes a continuous quantity, an infinitesimal quantity, shrinks down to where it has no dimension, right? But it still has dimensions of length, so don't worry about that, okay? So we have this. Here's our integral. Now, the thing you have to understand is, if you can do this for one simple trapezoid, that's all you need. Because if you can do it for one simple trapezoid, you can do this and write down the same expression for n trapezoids and their total. And that expression goes over to an integral in a very simple way. Now, in a theoretical calculus course, again, you spend some time totally understanding this, but it's plausible from the fact that you know if you did this for 1,000 intervals, you'd have very little error. Your approximate areas would be very close to the actual areas. Okay? Now, the only thing we're missing on the integral is limits. Okay? Well, the limits go back to the interval you partitioned, which is the interval over which you've revolved this So that's the integral from 0 to 12. And that's a really easy integral. Oh, man. I left the square off here, here, and here. I was so busy writing stars, I thought I was done writing exponents, right? But it's got to be pi times r squared to get the area of the cross section, right? I didn't realize it till I got down here. I've known all along that we're going to get a fourth power when we square this thing, right? So you just use distributive law to square this. You're going to get a constant term, a square, and a fourth power, right? And those are really easy to integrate. You don't have to use substitution. You don't have to use integration by parts. Just boom, 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 and that integral is trivial. And if you saw that integral on an exam, you'd be ecstatic. And you will see integrals that easy. Okay? So that's how you build up a solid of revolution. Now there's another thing you can do where you revolve it around the y-axis. And I'm going to ask you to think that through, but your book, of course, gives you good illustrations and tells you. If you understand this process, that's pretty much it. And it isn't that hard. But understanding it deeply and understanding why it works is a basis for tangibly understanding what an integral means. Okay? So it's a really good thing to understand whether you're going to ever work with volumes or not. Because what you do in setting up any integral is totally analogous to what we did here. You figure out what happens on a typical interval. You set up a sum, you write down your integral, and then hope that you can integrate it. And if you can't, you do it by approximation.